Hi everyone. So today we're going to be looking at a different conic section, one that I think most of you are a little bit more familiar with, which is the parabola. But what we'll see today is that in addition to the parabolas that you're probably used to graphing, the ones that are kind of either upward or downward facing, we'll see that we can also have sideways parabolas. And so we'll learn how to graph those today as well. And then we're also going to look at just a couple of applications. There's not going to be that much to say in this video about parabolas because, like I said, I think most people are pretty comfortable with graphing them. But I do want to show you a couple of applications, both related to parabolas, and then also I'll mention something related to ellipses as well. So I want to start by giving the geometric definition of the parabola. So remembering back to the last couple of videos, we talked about how for an ellipse, the ellipse was the set of all points such that if you add up the distance from one of the points on the ellipse to the distances to each of these other 2 points called foci, if you add those 2 distances up, you always get the same thing. And then we saw that for the hyperbola, it was basically the same definition, except for instead of adding those distances up, you're actually subtracting them. And so we'll see that the parabola has a very similar definition. So for the parabola, for both the ellipse and the hyperbola, they both had these 2 special points that were called the foci, which is just plural for focus. And I was watching a video today that actually pronounced it as foci, and now I'm like, I don't know if I've been pronouncing it wrong my whole life or what, but I'll still call it foci. For parabolas, there's only one point that's called the focus, but then there's this other line that is called the directrix. So let me draw a couple of examples here. So I'm going to draw one upward facing parabola, or one like vertically oriented parabola, and then I'll also sketch an example for a sideways parabola. So basically what's going on is that anytime you have a parabola, there's a special point associated to it called the focus. And so that point, again, just like with all the other shapes, it doesn't actually lie on the graph. It's kind of nearby, and it's just sort of this like invisible kind of scaffolding for the graph. So that point, as we mentioned before, is called the focus. And so for this one, the focus would be somewhere like around here. So for a parabola, instead of having another point that's also called the focus, they have this line that is called the directrix. So this line here is called the directrix. And if you were talking about a sideways parabola, then the directrix would be a vertical line. So basically for a parabola, if you choose any point that lies on the parabola, so say I pick a point here, if you were to add up the distance from the point on the parabola to the focus, and then add that to the distance from the point on the parabola to the directrix, or actually, sorry, I kind of phrased that wrong. So basically what I'm saying here is that the green distance and the red distance are the same. So I said something about adding them up that I misspoke. But basically, no matter where you choose, so let's say instead we choose a point like maybe here on the parabola, then this distance will be the same as this distance, which obviously I didn't draw it super well, but maybe I'll put these little tick marks to represent that fact. So basically, any point on the parabola is equidistant from the focus and the directrix. And then same thing with this other example. I'm not going to draw it on there because it's very similar, but I just wanted to show you how for a sideways parabola, the directrix is a vertical line. So a parabola is the set of all points that are equidistant from a point, a specific point called the focus, and a specific line, which we saw is called the directrix. So basically, if you just pick a point in space and pick a line, and you kind of find all the points that are equidistant between those two things, you'll always get a parabola. So just like what we talked about, in the other videos, this isn't super important for you to know. I'm not going to be like testing you on this. It's just kind of like background information. I do though want to talk about why is it called the focus, because I think it's actually kind of interesting. So this is getting in a little bit to like application. So why is that special point called the focus? So, when you hear the word focus, you might think of a couple of different things. You might think of like trying to focus while you're doing work. You might also think about, focusing a lens or like focusing light. Like focus is also used in the context of basically like optics, things involving light and stuff like that. I do not pretend to be an expert on this stuff, by the way, so I'm going to give you kind of my interpretation of things that I've learned, but yeah, I'm definitely not an expert. Let me just say that up front. So why is this point called the focus? So basically, if you have a, like, for example, a piece of metal or some other reflective material that's in the shape of a parabola. So let me kind of sketch an example here. So let's say that you have, this is some kind of reflective material and this is a parabola. I know it doesn't necessarily look like a parabola, but remember that parabolas can be really wide, right? Because you can, and we'll see this in a little bit when we get into graphing them, you can stretch them horizontally or vertically and basically get them to be either really tall and skinny or really like short and wide. And so this would be an example of a really wide parabola. So if you have something that is reflective, that looks like this, and maybe let's say that the focus is like here, there's kind of two different things that are true. So one thing that's true is, let's say that you have a light source at the focus. So you have some kind of like a light bulb at the focus. So if you shine light out of this focus, so imagine this light is kind of going in all different directions, right? Because it's just this light bulb that's kind of giving off light. The reflective surface of this parabola will actually reflect all of those light beams, or see, this is where I'm not an expert. This light, it will reflect all this light out actually in the same direction, kind of like straight out. So, I don't know the details of this, but I imagine that this kind of idea is used in a lot of like lamps and things like that, or like spotlights, where if you can imagine like having a light bulb and then having some kind of a curved surface next to it, it could really help you to direct that light to one specific place. So this example is, again, we have the light source at the focus, and basically just because of like the properties of the curvature of the parabola and the location of the focus, it allows that light to really come out in this special way. The other thing that's true, and this is what we'll see examples of in some videos in a second. So again, if this is a parabola and this is the focus. So now let's say that you're shining light into this rather than kind of out of it. So you have like light rays coming in like this and this and this and this, just sort of like ambient light coming in. So again, due to the curvature of the parabola, all of these light rays are actually going to bounce off in a way where they go through the focus. And so basically, why, like this, I think really gets into why it's called the focus, because all of these light, all this light is basically coming back to this point. It's all being focused on the focus. I drew these arrows to kind of keep going, but but all of this light is at one point kind of collecting at this point that's called the focus. So that's what we'll see a couple of videos showcasing. So let me pull that up. So the first one we're going to look at is, so this is a piece of metal that has been bent into a parabolic shape. And so this person is shining a laser, and they're going to be shining it like a laser pointer, shining it directly at the reflective surface. And you'll see, so the focus is this point right here. You'll see that the lasers literally go right through that focus. So you can see that it's bouncing off perfectly through that focus. And then, if you move the light elsewhere, so now this is straight down the middle, so this is going to kind of bounce straight back. But if you choose another place, you'll see again that it goes right through the focus. So again, it's kind of this relationship between the curvature of the ellipse and the location of that point. And so that's why that point is really special. Okay, so how can this be kind of like harnessed? Well, I'm going to show you a couple of examples that are kind of goofy, both of them, but basically both the examples I'm going to show you are going to have like a kind of a three-dimensional version of this, where you have a mirror that is, you'll see it's going to look more like a bowl or like a cup kind of, but it has the same kind of parabolic curvature. And so the first video we'll look at, someone is going to be using so here's the big mirror that has a parabolic curve to it. And basically the focus lines up to be right where they're going to actually cook some burgers. So we'll see that by just letting the ambient sun rays come in, because this mirror focuses the light, it's going to make this pan hot enough to actually cook burgers. So I'll link all these videos below, but you can already see there's smoke. Like, I just think that's kind of crazy. Let me jump ahead a little bit. So you can see they're like actually cooking these burgers. And sorry, my internet is very slow in my house. So if this stops going, then that's okay. I'll just link it for you to see. But basically they cook the burgers all the way through. So again, it's the kind of weather where you're standing outside and the sun doesn't feel like anything crazy, but if you can kind of focus the sun together all to this point, then that allows you to get enough heat to actually like cook. So one more example, kind of similar, although I feel like this video is a little bit less, it sounded like it was going to be really cool, but it's not as cool, I thought. But so this is, again, this parabolic mirror, and basically they're going to use it to melt an iPhone. So I'll just show you kind of the setup, and then I'll zoom forward because it's not as interesting as you'd think. So here they have the mirror set up, and they're focusing the light onto this, this phone. And let's zoom forward a little bit. So yeah, basically they burn and melt the phone completely. So if you want to check this out in more detail, I'll link it so you can look at it. But yeah, so basically that's why this thing is called the focus of a parabola. So one thing I wanted to mention that's kind of off topic, but like going back to ellipses, but it just feels like kind of the most natural point to bring it up. So the foci in the ellipses also have kind of a natural interpretation. So basically, if you imagine the planet Earth, or really any of the planets in our solar system, and think about what's the trajectory that they make when they orbit around the sun. So you might guess that it's a circle. You might guess that like, okay, maybe it's like the sun is here in the middle and the Earth kind of goes in this perfect circle around it. So maybe here's Earth. I don't know. I'm bad at geography. There we go. And that's actually what people thought was the case for a long time, was that the planets all orbited around the sun in a circular orbit. But it actually turns out that the orbits of the planets are ellipses. And the sun is not at the center of the orbits, it's actually at the foci. So this is actually not what the situation is. It looks more like this. And basically the orbits are actually really close to circular because, I'm actually not really sure, probably because of how big the sun is compared to everything else, but how massive the sun is compared to everything else. But yeah, it looks more like this. This is kind of an exaggeration, but the ellipse, or the orbit is elliptical, and the sun is actually at one of the foci. And that's going to be the case for any planet in the solar system, is that, they'll all have these slightly different elliptical orbits, but for all of them, the sun is going to lie at one of the foci of the ellipse. So this was, by the way, something that was discovered by, I know his last name. I think his first name was Johannes. I hope I'm not wrong on that. His last name was Kepler. But yeah, let me just, to be safe, let's just say Kepler's. And so I think it's Kepler's first law of motion. So if you want to look more into that, I'm sure there's plenty of videos on YouTube about that. And maybe if you've taken a physics class or an astronomy class, you probably know more about this than I do. And hopefully I didn't say anything that was horrifically off base. Okay, so that was just kind of our mini applications discussion. But now I want to get into actually graphing parabolas. So I want to start by graphing just really, really basic examples of parabolas. And we're actually going to make tables, even though you might feel like you don't need one, just to really be able to kind of compare and contrast a couple of examples. So yeah, so we're basically going to sketch the following. Parabolas. So first one we're going to do is going to be y is equal to x squared. So, I think you all hopefully pretty much know what that looks like, but I actually want to make a table just for the sake of comparing it side by side with the one that we're about to do after this. So how would you make a table for this? Well, you'd probably want to plug in some different values for x and see what you get for y. So for example, you could plug in -2, -1, 0, 1, and 2. So if you take each of these numbers and square it, you get 4, 1, 0, 1, and 4. So that's going to give us a graph that looks something like this. So I'll just plot a couple of these points here and then kind of go from there to sketch the graph. So, and then it also goes through 3, 9, and -3, 9. So something like that. So that's kind of our standard parabola. So what if I now, instead of graphing y is equal to x squared, what if we switched it up and did x is equal to y squared? So what is that going to look like? Well, let's make a table. And when we make this table, it kind of makes more sense to actually put y on the left and x on the right, right? Because it's like, if you just think about the way this is set up, we want to plug in all different numbers for y and see what we get when we square it. So if we set this up as, y is equal to -2, -1, 0, 1, and 2, well, x is equal to y squared, we just square all of these. So our table basically looks the same as the table that we had in the other example. It's just that the x's and y's have switched roles, which might sound kind of familiar to you, right? That kind of sounds like inverse functions. And so we'll see that there is a relationship between these, although we'll see when we graph this that this actually is not going to be a function. So it's technically not the inverse function of y is equal to x squared. So what's this going to look like? Well, it still goes through 0, 0. If we go to a height of -1, we're supposed to have an x value of 1. So we have this point here. If we go to a y value of +1, we're also supposed to have an x value of 1. So we have a point there. If we go to a y value of -2, we're supposed to have an x value of 4. And if we go to a y value of +2, we're also supposed to have an x value of 4. And then it will also, both of them will also go through 9, 3, and 9, -3. So we can see that we get basically just a perfectly sideways version of the parabola that we already graphed in blue. So one thing I just want to point out about this graph is that is the relationship between this graph and the graph of y is equal to square root of x. So just kind of as a side note, if you were supposed to graph y is equal to square root of x, that would just be this part here. So this green part would be y is equal to square root of x. And then if I did y is equal to negative square root of x, that would give me the bottom part. So those are functions, right? Those, you could say f of x is equal to square root of x, f of x is equal to negative square root of x. But when you put them together and make this sideways parabola, you know, individually they are functions because they pass the vertical line test, but once you put them together, this graph is going to fail the vertical line test. So sideways parabolas, just like a lot of the other conic sections we've looked at, are not functions. Okay, so let's look at a few other examples. So I want to basically just do some kind of transformations to, some very simple transformations to each of these graphs. And what I would say is basically when you're graphing a sideways parabola, personally, at least the way that I think about it is I kind of translate it back to and kind of imagine that it was just like a normal vertically oriented parabola. And kind of think about what would it look like that. And then you can just take that graph and basically all you're doing is you're switching the x and y coordinates. Or you can think of it as you're taking the graph and you're reflecting it over the line y is equal to x. Right? If you were to put the line y is equal to x here and take this blue graph and flip it over, it would give you the purple graph. And you might remember that that was how we found the graphs of inverse functions. Again, that doesn't quite make sense here because this purple graph is not a function, but you know, if it was, then that would make sense. We're going from one to the other by reflecting over the line y is equal to x. Okay, so let's do y is equal to let me move this down a teeny bit actually. So let's do y is equal to negative x squared. And then after that, we'll do x is equal to negative y squared. So what does y is equal to negative x squared look like? Well, we're basically just going to take this graph and we're going to reflect it over the x-axis, right? It's a vertical reflection. So it's going to look just like the graph that we had above it, but now it's going to be upside down. So I'm just plotting some points here. And it's going to look like this. Okay, so not my best work on drawing this, but you get the idea. So what's this other one going to look like? Well, I think the easiest way to understand what this graph is going to look like is just to kind of take the picture that we have here and kind of translate it by either switching the x and y coordinates or by flipping over the line y is equal to x. So personally, I tend to prefer to think of switching the x and y coordinates. So whereas this point had, or the graph of y is equal to negative x squared had points like -2, -4, this one is going to have graphs like -4, -2. So if we basically go through and take each of the points, so 0, 0 is going to stay the same. And then the points that were here and here are going to now be here and here. And then the points that were at 2, -4, so that's this point here. That was probably a mistake. Okay, there we go. I have to make sure I make it big enough that I can erase it. So the points that were at 2, -4 and -2, -4 are now going to be at -4, 2. And, oops, that was not -4, 2. That's here. And -4, -2. And then finally we have one at -9, -3, and -9, +3. So that's going to give us a graph like this. So basically what happened here is that this negative sign actually flipped it now over the y-axis. But I wouldn't try to like memorize that as some new rule of like, you know, how these transformations work. It's more like, I think if you can just visualize what, you know, what y is equal to -x² looks like, and then just kind of translate that like to switching the x and y coordinates. Okay, a few more examples. So next one I want to do is going to be y is equal to sorry, I like to be consistent with my notation. I guess I said example. So let's do y is equal to 2x². So what does that look like? Well, basically you can think of the 2 here as being a vertical stretch. So why is it a vertical stretch? Because you're not multiplying x by 2, you're multiplying kind of the whole thing by 2, right? If it was like this, that would be different. Then you could interpret it as being something horizontal. But in this case, because it's 2 times x², this is a vertical stretch by 2. And so that tells us that our graph is going to look like our original graph, except for all of the points will be lifted up, multiplied by 2. So, you know, you're welcome to make a table, plug in points, but I think honestly, it's probably a good idea just to kind of have some of the points on the standard parabola memorized, because then it makes it really quick to graph these transformations. So I like to just kind of have in my head, you know for sure, like kind of what the shape of like the original or the kind of the first few points are. And that way I can just go directly into graphing the transformation. So it's going to be at 1, 2, -1, 2, 2, 8, and -2, 8. And so this is what our graph will look like. So vertically stretched upward, kind of skinnier version of the original graph. So now let's do x is equal to 2y². So basically it's going to look just like the graph that we just graphed in blue, except for now it's going to be sideways. So instead of having these points here, they're going to be here and here. And then instead of having these points here, they're going to be here and here. So just kind of switching everything, making it sideways. And so what ended up really happening with that too? Well, it ended up actually being a horizontal stretch. But again, I don't want you to think of this as like new transformation rules that you have to learn, because I think it can just get really confusing when we're changing things to no longer be functions. It just, the rules that you might have learned before aren't going to quite translate maybe the way you expect. So I wouldn't think of it that way. I'm just kind of writing it down. Maybe you know what, I'm just going to erase this because I don't want that to be the way you think of it. I think, think of it as your original function, and I'll erase this too. And then just see what that kind of gives you when you do the translation to being sideways. Okay, one more I want to do. So let's graph y is equal to 1/2 x². So what's that one going to look like? Well, this one is going to have a vertical compression by 1/2. So instead of having the points that it had before, each of those points is going to be multiplied by 1/2. So the points that used to be at a height of 1 will now be at a height of 1/2. The points that used to be at a height of 4 will now be at a height of 2. The points that used to be at a height of 9 will now be at a height of 9/2, which is 4.5. And so we'll get a graph that looks something like this. So similarly, if we then go to graph x is equal to 1/2 y squared, well, it's just going to have that same shape but sideways. So now we have points that are at an x value of 1/2, and then we have points that are at an x value of 2, and then we have points that are at an x value of 4.5. And so that gives us this shape. So really, we're not going to be doing anything too crazy with these parabolas. It's just basically, you'll see this come up probably in Calculus 2, that you're going to want to have some familiarity with graphing, especially parabolas when they're given to you in terms of y instead of in terms of x. So basically just simple stuff like this. And then in tomorrow's video, we'll also talk about horizontal shifts. So we'll do that not only with parabolas, but with kind of all the shapes at once, and because it's basically the same logic for all of them. So yeah, so we'll see a little bit more of parabolas tomorrow, as well as the other conic sections. All right, that is it. I will see you all next time.